So for this placement, the order will be like this. So these VDD center, okay. So it will be, the V will be like this, okay, here like this, here like this. Similarly in this section, because we have few grounds here, and then we'll start the component placement. So during the practice, I would suggest just don't get frustrated, because it is a bit time taking. Maybe several times you have to delete things. Let's place those quickly. And just select the components. And start placing those. So just follow the plan, whatever we have planned. It will be like this, one will be like this, another one here. Okay, you can't place one here because, okay, we can remove that because it is just extra part of the thing. Another one will be here. Now these bigger ones, so for those just follow this empty space here. Here we go, right? So to remove this problem, yeah, so this was just the extra stub there, right? Let's move to the another one. So what is the left here? Okay, there's one more issue. Just save the file. Okay, I guess we have covered all the 5 things, right? So again, this is the most difficult part of the placement, or you can say the routing or BGA fan out, because here you have to just fit, you know, all these components. Apart from that, these are just spreading things, and here you have to just place the stub and just connect those directly, right? For example, these ones, so these are the outer component, okay. So here you don't need to worry about, here we have few more component to place, because here we have all the connections, and there will be some blind vias, right? So those is, you know, the other side of those via is not, you know, opening at the bottom side, so you can place components there at the bottom end. So let's demonstrate that as well. So for that, just target this one, LPDDR4. I'm just going to place one section, okay? So let's suppose this one. So for before that, just, you know, place the fan out. So here you can see, so we can't use ground of these section, right? Here, these ground. So these grounds are given for these inner, you can say the power pads, right? But there is again a complete ground section is given in this section, right? Here you can see that, right? So the placement orientation will be, the power pad will be at this side, and the ground pad will be the other side, okay? So again, copy it quickly, Control C, and start placing those. Okay, so here it will be like this. And these will be directly connected, okay? Now Control C. So here we don't have space to place VI in this direction because it will be over the ground pad, right? And here we have to place the pads for ground as well, because when we place it like this, there will be very less clearance between the ground and this pad, right? So to avoid that, because these are all the bigger component, they just skip one pad here, right? So that is the bad thing about the bigger package. Again, just quickly place those. Similarly here. So again, this is the easiest placement and routing, because these are the outer section of the fan out. And again, just apply the filter, select these components, and just place those quickly. Okay, so this is the one section. The another section will come in this direction, right? So that you can try. Okay, so this is all about you know, the placement and the fan out of all the supply pins for the system on chip. Now let's discuss the another topic. So again, this is again a part of assignment. So what I will do, so if you remember how we started at the beginning, all the component were placed in this section. Okay, so for practicing this particular session, I'm going to share that as well. Okay, apart from that, after few hours, like after the video will be uploaded, I'll share the another zip file, and that will be the complete routed section of this portion of the SOC. Okay, so that you can use for reference, and during the practice maybe you need it in case of any confusion or something like that. So here we have some space left that you can use for these components. Should be again pretty directly connected, right? So you can do that. Let's move to the another section. So let's mark this one quickly. Okay, anyways, so okay, so another part is prepare the impedance profile for all the high speed tracks. So what is impedance profile means? Okay, so as I said, we are using a 12 layer board, right? And for a particular, or for maintaining the particular impedance, so again, for 12 layer board, layer 1, the gap between layer 1 and layer 2 is different, right? It can be different, it can be same for all the layers, it depends on your stack up, right? So let's suppose it is different, right? So that is what we do. We basically tell the layer stack up for this particular impedance. I just want to maintain that impedance throughout any signal layers, either it is internal or external, anything, right? So to do that, we basically define the impedance profile. So again, the procedure for defining the impedance profile is, first step is we have to note down what are the types of impedance that we're going to use in our high speed tracks. So the first thing will be type of impedances that we're going to use. Okay, and for that, as I already told you, we have prepared an impedance table, right? So on these impedance table, you'll see you have 100 ohm, you have 50 ohm. Similarly, you have to just go through with each and every interface that we are using, and you'll find only 3 types of impedances that we're going to use. The first one is 100 ohm, and that is differential. Another we're going to use 90 ohm for USBs and Type C, and that is also differential. Another one we're going to use is 50 ohm, and that is for single ended, right? For SDMMC, for eMMC, like that, right? And that will be single ended. Okay, so we have to define those. So to do that, firstly I'm going to merge that, open the PCB file and go to the design and layer stack manager. Okay, so this is the layer stackup that we have defined, and here you'll see three options. So we have already used two options. We have defined the VR types. Okay, we have defined the stackup. Now we're going to use another tab, that is impedance. Let's click on this one. Now you'll see this type of window here, right? So again, this add button, this remove button is a part of this impedance profile tab. Okay, now click over add profile. Maybe you people have gone through with this one. So this is pretty simple. Now here you have to mention the description, like which type of impedance we're going to use. So let's follow this one. Let's 100 ohm, and this is differential. Now another thing is, after writing the description, you have to select the type. It is differential. Here you have to mention the target impedance. So in our case, the target impedance is 100 ohm. Here you have to mention the tolerance. So that tolerance we're going to follow is 1%. Okay, that's it. Press enter. Now here you'll see, so you're not seeing all the 12 layers here, right? You're seeing only the signal layers that we are using. For example, top layer, L1, L2, L3 and bottom layer, right? So when I'll select the top layer, it will choose 2 layers. So what is the meaning of that? The meaning is, as you can see in this section, so again, what is, when we do anything related to impedance, okay, so there is a role of return path as well, right? Or you can say the gap between the return path, what is the dielectric properties, these all things define the layer, the impedance of the track, right? So here this ground is the return path of top layer, right? Similarly, if we go to this one, the L2, so you can see we have 2 return paths. One is ground 2, another is ground 3. So wherever the signal will find low impedance, it will choose that return path. Similarly, for this one, if you'll select here, we have 2. For this, same thing, right? And for bottom layer, we have again ground 5 as a return path, right? Now when I'm shifting between the layers, you'll see these properties are changing, right? Because of some internal properties, or they have multiple grounds. One is core and one is prepeg because of their property as well. So here you can see, so again, this is the gap. Gap is, for differential pair, we have one positive signal line, one is negative signal line, right? So gap is the gap between those tracks. Okay, what are these W2 and W1? You can see, so again, this is during the manufacturing, we have to follow the W1. So the W1 is 1.9 mil. Okay, now here you'll find, if you'll just hover the cursor over this one, and you'll see calculate the trace width with respect to like calculate the trace width automatically. Okay, and this gap is fixed. Okay, so here you have to verify, this is very important, you have to verify that your with your manufacturer, I want the routing width on the internal layer 1.9 mil. Okay, so this is very thin track, and you have to verify. Okay, now you have to change that. So how you can change that? Let's suppose I asked the manufacturer and they said, okay, I can go for 3 mil. Okay, below 3 mil we can't manufacture, and you can't able to get any other manufacturer to, you know, for this special requirement. So for that, what you have to do, you have to just adjust the trace gap, and this width will be automatically calculated. Okay, so for that, let's make it 8 mil, and you can see the width is increased now. Okay, and the impedance in this case is 100.03 ohm, right? The deviation is 0.03%. So this is like very accurate calculation. Similarly, if I'll go for 10, you can see it is again going nearly to 3 mil. So in our case, we're going to follow the default one, 5 mil, because I've already confirmed that they can manufacture. Either we can go for PCB way or next PCB. We have 2 options, and Yeah, that is the thing. uh, yeah, that is one thing I wanted to tell you. Okay, so let's create another one. So this is our one impedance profile for 100 ohm impedance. Now we have to connect two more. So for that you have to click over the add button. Now here we go. So again this will be diff 90 underscore yeah, it is just 90 ohm differential, right? Select the differential, put the target impedance 90 ohm, make it 1%, enter. So again I don't need to check for this as well, because when we increase the impedance, the width of the track will decrease, right? So for this one it will be, again it will be higher, it will be around, so as you can see it is by default 2.7 with 5 mil clearance. But when the impedance was higher, with 5 mil the gap was the width was smaller, right? So when we go for the lower impedances, the width will increase, so we don't need to worry about here. Now let's add another one quickly, and that is the 50 ohm single ended. So that will be 50 ohm underscore single ended, and here you have to type the single here. This will be 50 ohm, that will be 1% again. Enter. And for them, I mean for this one the track width is little bit higher, right? Because we are going for 50 ohm impedance. Okay, so these things are, just save the project file. Now the task is not completed yet. We have to assign those impedances profile to different net classes that we have created. Okay, so this is again a part of your assignment. For that, let's start with, so again we'll just go through with each and every schematic and we'll see for what we have to assign those. So I know that things will start from this one. The first page will see where the impedance definition required, that is 50 ohm SDMMC. Okay, so this is the net class, and for that we have to assign the impedance profile of 50 ohm. How to do that? Again, go back to your PCB, go to the design, rules, again go to the width, add new. So again, how I know I have to just add the width here? Because see, for 50 ohm differential, the width is the only factor that is varying, right? And we have to assign that for SDMMC. So let's do that for SDMMC. Width, you can rename it anything, right? So just follow the same standard for all the things. Okay, and this is our default thing. Here we have changed the width to SDMMC, and I'll show you, you can adjust the priority as well. Now here you have to select the net class, because we have already assigned the net class for SDMMC, and this is this one, right? 50 ohm SDMMC. Let's select that. Now here we have, either we can go for manual entry of all the layers, or we can just use the impedance profile of 50 ohm, right? 50 ohm single ended, that is what we have defined, right? And apply it. Okay, so I'll just show you how is it applied or not, or there is any problem with the width. Okay, so let's split the screen, go to the SDMMC page, see which are the, okay, so these are the connections we have. Okay, you can do one more thing. To select all these together, go to the PCB tab, and if PCB tab is not here, you can just open that from here. From here select the 50 ohm SDMMC, so it will be like automatically selected. So these are all the connections that we have to verify. Now I'm just going to try with the routing. So let's route those. VIA properties are not defined for them, so let's switch it to some internal layer. So how to do that? There is another way to switch between the internal layers, and that is only happen if you defined the VIAs, right? So if you remember, we already defined. Now press So again, what is the next signal layer we have? So you will see we have next signal layer on layer number 6, right? So just draw that and press 6 on your number pad, and you can see we have switched between the layer, and now the width is different, right? Because of the internal properties are different. Similarly, now we have to switch between the, so again that is not possible to switch between the bottom layer because it is going like very high, it is 12 layer. So for that you have to start from bottom layer and just go back to layer 6 again, and you can just route like this. Okay, so again these are not the size of via we're going to use. I'm just demonstrating here. We have implemented the impedance profile for SDMMC. So that is one thing, and this is your next assignment. What you have to do, I'm just going to demonstrate for differential as well, one differential, then you can do it by yourself. So let's suppose I have to define the PCIe express. Okay, and I guess this is again the error that we repaired yesterday. Okay, let's do, I'll correct that, and let me note it down. So correct the error on PCIe differential. Okay, I'll do that. Let's take something else. Let's take HDMI as an example. Here we go. So I'm just going to define the impedance profile and all the design rules, especially for the width and gap for the differential pairs of HDMI. So for that, what you have to do, just procedure is same. Firstly, just remove the highlight, go to the design rules. Now instead of adding width here, there is a separate section for differential pairs, and which is here, right? You have to add new rule in this section. That is for HDMI diff. Okay, now from here you have to select the differential pair class, and in our case that is diff under HDMI. Okay, use the impedance profile, and here you'll see two options because we have defined the differential pairs for 100 ohm and 90 ohm. So whatever we will select, the width and the gap will be defined from that profile. So in our case it is 100, and just apply those. So it is that easy to define or to design to create the design rule for all the differential and single ended wherever the impedance is required, right? So through that procedure, we can able to define what is the width and gap required. We can able to define the design rule for all the high speed tracks. Okay, whatever the high speed track that we're going to use in this SOM board. So let's quickly just check if it is fine or not. So where are those HDMIs? So for those you'll not find those here. So you have to just click over the differential pair editor, and there you'll find differential 100 for HDMI. So again you'll find option because PCIe also have the same net class. I'm just going to correct that, but here we have these HDMI connections. Let's check quickly. So you can see this is the top layer. Here we have to place some VRs to avoid the problem. Let's see if we can place it. Okay, we can try with those. So again you can see we can shift it to layer, and again these are not the VR that we're going to use. We're going to define the VRs for all the signal tracks and high speed tracks. But yeah, you can see we have defined that for HDMI as well. So just press Ctrl Z. Yeah, so that is again a part of your assignment. So this is the whole thing for today's session, and you have to just do that. I'll share all the documents, and just take your time and practice things. And in next session, as I said, we're going to route all the high speed tracks, and we'll implement these design rules, as you can see. So till here we have implemented only this one, right? Apart from that, we have few more design rules to implement. For example, this one, the pair to pair spacing. What will be the spacing between the the differential pairs of pair. So that means like differential has multiple TX and multiple RX, right? So every RX and every TX has its own pair that is positive and negative, right? So what should be the gap between those? Okay, and these are all the things we have to implement on the clearance section of the design rules, right? Similarly, what should be the gap between PCI and the other interfaces if we are going, if those tracks are going parallel, right? But before that, we will do the layout planning, which is very important. So we will see on which layer, because we have 3 internal layers to route all the things, to route all the high-speed tracks, which is we have a lot of space to routing. So we'll basically assign those layers so we can able to minimize. So as you can see, not in this case, but here the length of the track is also a constraint. So for example, they are saying including the package, including the breakout, including the layer or on which layer you're routing something, the length of the track should not be greater than 1500 mil. Okay. So during the length matching, we have to take care of that. So when our straight connections will be like very small as possible for all the connections, all the byte groups, only then we can able to maintain this, because otherwise we have to just keep deleting tracks and try to implement the design rule. That is what the advantage of models, right? Because on model, we don't need to exactly follow the design rules, because we can always route the tracks and go back to the hyper Linux and check for, okay, is there any problem, we are seeing any skew on the line, or is there any timing problem with the reference signal that we are using, for example data strobe and the data signals, right, address and command and the clock. But in our case, we have to design the board ideally, so we have to just follow all the design rules. Anyways, so this is the session for the day, and till here, any doubt?